the people join. So, Mr. Guru Prakash, as you informed to all the class, we'll have tomorrow one class, only one class. I don't take more than that. But if you are willing, we will take. Otherwise, I'll just keep myself till 8:30 to 9:30. Okay. So please join me tomorrow so that we'll try to finish off some problems and all. Because I already put one assignment. It is due on 30th, I think. So some problems, a lot of problems I gave. At least some problems I have to show you how it should be done. Then only it will be interesting for you to at least see and write. Okay. So we'll do some problems today before we go to that recycle reactor. We'll do some 2-3 problems. How many is comes into today's period? We'll see, so that you'll feel comfortable in doing the other problems. Rest of the problems will be similar in kind, right? So is it okay, Guru? Shall we do problems today? Next class, maybe Saturday, we'll complete that recycle reactor. Okay. Guru?
Okay.
Okay. Okay. Now we'll do. I think my screen is visible for you. Just I'll show you. Okay. Is this my screen visible, ma? Yeah. You just see. This is what yesterday we are discussing. Reactors in series, parallel. Generally, parallel reactions we won't go. But the important thing in parallel reactions is the flow rate should be divided by the number of the reactors. That you remember. This only 2 marks they'll ask. They may not ask even the problem also. Only if you are doing some MTech course and all, then they will ask you problems. But as far as the university exams are concerned, I think they'll just ask some 2 marks or something like that. How this flow rate should be divided. The flow rate should be divided according to the number of the reactors. If there are 4 reactors, this flow rate should be divided by 4 for the each one. Okay, that you remember, right? So let us see some problems. So to feel comfortable, I hope I'll do these 2 problems today. Still a lot of problems are there, almost a similar kind. So first 2 problems I'll solve, then you can do the rest of the things looking at Kavani book and all. So if you are having the notebook with you, then if you can write, you write. Just I'll read the question. Let's listen to it carefully. The elementary liquid phase reaction A plus B gives R plus S. So he himself giving you liquid phase elementary. That means that it is second order. So he himself is giving you that. It's a liquid phase, so no need of you for having the expansion factor into picture, right? The elementary liquid phase A plus B gives R plus S is carried out in a PFR. So you have to use the PFR performance equation. So concentrate on whatever the colored marks, so that is important, right? So A plus B gives R plus S is the reaction in a reactor called PFR. For equimolar amounts, that means the amounts of the concentration of A and B or moles is same. Ca naught is Cb naught, that is the initial concentration of A and B is 0.9 mole per liter. 94% conversion is achieved in it. So 94% conversion is achieved with this what do you call equimolar initial concentrations of this reaction in PFR. Now, if this PFR, if a CSTR 10 times as large as PFR, so he is removing PFR and putting CSTR, which is 10 times larger than PFR. We don't know the volume of the PFR initially. We have to find out. So it was replaced, that PFR is replaced by a CSTR, which is having 10 times as large as PFR, were arranged in series with the existing unit. So it is arranged in series. Some questions will come as it is replaced. That also you can do. That I think it will come. But here, 2 reactors connected in series, one PFR. The second one 10 times larger than PFR, which is a CSTR, is connected in series with the existing unit. which unit needs to be arranged first in series to enhance the production rate. So he is asking you whether PFR plus CSTR is good or CSTR plus PFR is good. So you have to do the both the cases and then find out in which case your conversion is increased. Your conversion is increased, right? So you understood the problem? One PFR is there. So you want to enhance the production rate or conversion or whatever it is. So he is trying to use one more reactor which is 10 times larger than PFR. He is not using a PFR, he is using MFR. He is asking you whether MFR should be connected first or MFR should be connected after PFR. Right? Any doubt in the question? You understood? So write the given data and then PFR design expression. This is an elementary reaction. So we'll just go to that solution page. Yeah, we'll just go to the solution page. This is the same solution which we are being asked. A liquid phase elementary reaction A plus B gives R plus S is carried out in a plug flow reactor. For equimolar amounts of A and B, Ca0 is Cb0 is 0.9 mole per liter. 94% conversion is achieved. If a CSTR 10 times as large as plug flow reactor is arranged in series with the existing unit, which unit needs to be arranged first in series to enhance the production rate, right? So I'll do with the plug flow first because initially there is a plug flow, only plug flow. So we know that plug flow design expression is tau is V by V0, that is the volume by volumetric flow rate is tau by Ca0, right? So Ca0 I'm taking this side. Ca0 0 to XA dXA by minus RA. dXA by minus RA. Right? dXA by minus RA. This C0 is coming from this, right? This C0 is coming from this. Tau by Ca0 is this particular thing, right? So sticky note. We can put sticky note on the edit the image. Okay, let us put this itself. Oh, did I skip a lot of things? Yeah, here. Lot of things is skipped, huh? Okay. We'll come back again. It's 4.7. Yeah, in this book, he gives a lot of problems, solutions. It's a good book. So try to do the solutions. Some solutions may be wrong. Don't go blindly by the solutions. Some solutions are wrong, right? So when we studied in IIT Madras, we used to solve this entire Levenspiel book, you know, the Levenspiel, the exercise problems. Even I am having the solutions of what I myself wrote. Right? So these are beautiful problems, Levenspiel, right? The same problems I am just showing you here. Here, yeah. This is the tau by Ca0 is integral 0 to xa dxa by minus Ra. Now this is equimolar liquid phase. So A plus B elementary reaction. Therefore it is a second order. Minus Ra is K into Ca into Cb. Since A and B is equimolar, either you can write in terms of B or in terms of A, right? So if there is a difference in equimolar, then Cb0 by Ca0 you can put as M, and then you can eliminate B, right? So you can write only in one particular thing. Since it is Cb is Ca or Cb0 is Ca0, I can put K into Ca square. I can substitute Ca as Ca0 into 1 minus Xa whole square. So if I substitute minus Ra is this, tau is Ca0 by K Ca square because this K Ca square is there. which is a constant. I can take outside the integral dxa by 1 minus xa whole square. This a naught and this a naught get cancelled out. This a naught and this a naught get cancelled out. You are left with tau is equal to 1 by k ca naught integral 0 to xa dxa by 1 minus xa whole square. Right? That is what we'll do here. So what is the integral for this? Integral for this is 1 minus 1 by 1 minus xa. Right? Because the differential for this is should be this. So you put a negative here and you put a negative here. Then it will come as minus 1 by 1 minus xa. That is the integral for this. Here already one negative is there. Negative, negative, it becomes positive. Right? So don't expect me to do all these integrals because these are all is the basics. How you are getting from this to this, don't ask me, right? It's difficult for me to again start telling the integrals and all. You should know these are all some school stuff, +1, +2. You substitute the limit from 0 to xa. So if I substitute, the upper limit is this. Lower limit, if I substitute, this is where the people will make wrong. You think that 0, if you substitute, it becomes 0. It is not 0, only this value becomes 0. So 1 by 1 minus 0 is 1. This one, lot of people will not write. They just put this particular thing, you just substitute the upper limit. You have to substitute the lower limit also. If it is 0, it is fine, but it is not 0, only this value is 0. 1 by 1 minus 1, 0 is 1. This is where a lot of people may do mistake, especially for a second order equation. Again, I repeat to you, lot of people, because when we go for a paper evaluation, we see a lot of, because you need to do a derivation for this and then only do that problem. So this one, lot of people put, forget, then they put this integral is 1 minus xa, which is wrong. Then if you take the LCM here, it becomes only xa by 1 minus xa, not 1 by 1 minus xa, because you have to substitute, subtract 1. So we know that ca naught is 0.9 and xa is 0.94. That is what he gave. Just substitute it and then you can find out the k. Tau in terms of k. K he didn't give you, right? K he didn't give you. So substitute it. Now you are getting tau in terms of k. But we know that tau is V by V naught. That is volume by volumetric flow rate. That is equal to 17.1 divided by k. So volume, you can write volume I want. So 17.1 V naught divided by k. So this you keep in mind because this is the volume of plug flow reactor. No need to calculate the volume because he didn't give you what is V naught and what is k. If we give you substitute. But what is the next thing? He is replacing this. Or is having one more CSTR, which is 10 times large as the plug flow reactor. Now you know the volume of the plug flow. You know the volume of the plug flow. What will be the volume of the mixer reactor? This is nothing but 10 times V. That is nothing but 10 into this particular thing. That is the volume of MFR. That is what he is giving. Vm is 10 times Vp. That is given. That is nothing but this particular thing. Don't try to calculate this V naught and K because we don't know, right? So it gets anyhow cancel out and all. So keep it like that. Now we have to consider CSTR and PFR in series. Now we know the volumes of both the reactor. This is a plug flow reactor and this is a mixer reactor. Now we need to connect these two in a series. Either MFR will come first or CSTR will come first. That is what we need to find out. Let us have first case as PFR followed by CSTR. Let us use this particular thing. In CSTR, in PFR, you are having a conversion of 0.94, right? So it should enhance because you are adding one CSTR to it. So this is the PFR and this is the reactor which is being connected, right? So how much is going to come? That is what he is asking you, right? Okay. So performance equation of CSTR is this equation. We know that. What is CSTR equation? Tau by CA naught is XA by minus RA. XA is nothing but XA1 to XA2 because the input to the CSTR is X1, right? And output is X2. That is what? See, X2 minus X1 by R2. That is nothing but the rate here. So what is R2? R2 should be evaluated at X2. That is the conversion because conversion is X2. So X2 conversion, you will have some concentration. Based on that concentration only, your R2 should be evaluated. So in series, PFR followed by CSTR, X1 is the intermediate conversion and X2 is the overall conversion. So we can put this is the volume, this is the volume, this is the volume 174, yeah, 174.1 V naught by K. This is nothing but the volume of MFR is C naught X2 minus X1. This is the thing I'm just writing. X2 minus X1. V I am substituting V as this. V naught will be the same because V by V naught, right? This is nothing but tau. So these two get cancelled. C naught into X2 minus X1 divided by RA2 is nothing but at C2 or C this particular thing. So K C naught square into 1 minus XA2 whole square. You can write C as or C as C naught into 1 minus XA. We are writing based on the second equation, therefore X2 will come. Correct. So this V naught and this V naught get cancelled out. And you are left with 174.1 by K into KK also get cancelled out because here K, here K. So on the LHS, you are having 174.1. On the right hand side, you are having C naught, this C naught and this square also get cancelled out. So you are left with C naught 1 minus XA square on the numerator as X2 minus X1. You take cross multiplication and make as one equation. So 174.1 C naught 1 minus XA square is X2 minus X1. So get all the X2's to one side. We know what is X1. X1 is nothing but 0.94. That is what the conversion in the PFR. So you can put 0.94 X1. X1 is 0.94. Then try to calculate X2. This is a binomial equation. You get X2, two values of X2. I think one value you are getting positive, maybe other value negative. So generally conversion will not be negative. So you are taking a positive. So conversion is 98.33. So from 94, it is moved to 98.33 just by arranging PFR with CSTR. And again, CSTR is 10 times larger than PFR. Even though you are putting CSTR, which is 10 times larger, you are not getting much more conversion. Am I right? 94, 96, right? So we have to see the second case, whether you are getting this or still more, right? So by arranging reactors in series, PFR followed by CSTR, the conversion increases from 94 to 98.33. What is the percentage conversion? The conversion what you got, initial, final minus initial by initial, 4.61 percentage is increased. Your conversion is increased by 4.61 when you connect CSTR with PFR. And again, CSTR is having a volume of 10 times larger than PFR, right? So remember it. Now, second case, let us do CSTR followed by PFR in series. CSTR followed by PFR in series. So CSTR design expression is tau is V by V naught. C naught into X1. I'm putting X1 here. Earlier case, I put X2 minus X1 because the inlet for it is, yeah, where I put. Yeah, here X2 minus X1 I put because the CSTR is second earlier. So the inlet is X1 and outlet is X2. But now the CSTR is first. Therefore, initial X0 minus X1, X0 is 0 because there is no conversion. Therefore, only X1 will come by R1. Earlier, I am putting R2. But here, this is the first reactor, therefore R1. V by V naught is C naught. X1 by R is nothing but K C naught square into 1 minus X1 whole square. This is nothing but a second order. I'm just substituting minus R is KC into 1 minus XA whole square. Now, what is the volume? What is the volume? 10 times volume. So this is the same thing. Volume of a reactor is, yeah, this, right? 10 times volume. Where is it? Yeah, this. This is the volume of the reactor of MFR. So this is the same thing we'll put. 174.1 V naught by K V naught, because this is the volume of the MFR, is X1 by K C naught, because C naught and this square and this thing get cancelled out. This get cancelled out, right? So K C naught into 1 minus XA whole square. This V naught, sorry. This V naught and this V naught also get cancelled out. Whereas this and this get cancelled out. So 174.1 divided by K, again K and K gets cancelled out. So you take this 171.4 C naught 1 minus XA whole square is X1. Now this is say again by what is it? What do you call? What is called this equation? Double equation, binomial. It's a binomial equation where you get two roots. Yeah, this is a binomial. Minus b plus or minus root b square minus 4ac. So you can calculate X1 as 92.3 conversion. Here itself you can find out that MFR, if you put a PFR, you are getting around 96 conversion. But when you are putting MFR, it is just 0.92, 0.93, right? So X1, you know, now you put a PFR in series. Tau is V by V naught, C naught into X1 to X2. Earlier you put 0 to X1, but here PFR is the second. Therefore, X1 to X2 dx by minus R minus R2 actually here, right? 2, it should come. So V is substitute. This is the V, 17.41 V by K, and V naught is V naught. C, this is the second order equation. X is nothing but a final X, that is what he is giving. X2 is not giving, final is taking as X, or you can, if you want, you put X2 also, that's up to you. So this V naught and this V naught get cancelled out. This K and this K also gets cancelled out. You are left with 17.41. Here C naught and this C naught also cancel out. Only C naught is common here. You take it out and then put this side. 17.41 C naught integral x1 to x dx by 1 minus x, right? 1 minus x. If you are having x2 here, you have to put x2 dx2, right? So that's up to you how you want to put. So the integral for this is 1 by 1 minus x. You have to substitute the limits of x1 to x2. So if I substitute the limits, 1 minus x2 minus 1 minus x1. So x1 we already know 0.923. So you substitute, C naught is already known. If you all substitute, x2 is 965. X2 is 965. That means 96.5% conversion. So with this arrangement, CSTR followed by PFR, your conversion is only this. How much it is increased? This is the final. If you put only one particular thing, it is 94 by 94. Only 2.66% is only increase. Whereas the previous one, you got a big jump, right? We got 4.61 jump. So what reactor should be connected now? So for the PFR and CSTR, it is this much. And for this CSTR and PFR, it is only this much. It is clear that to enhance the production rate, PFR is first put and followed by CSTR. This is what in 11th bill he gave. For any orders greater than 1, the best combination will be to connect For any orders greater than 1, this is the thing which last class I'm showing you. Yeah. For any orders, yeah, where is it? Here it is not there. Yeah, you can see here. For any orders greater than 1, the curve, where is it? There should be ordered to keep the concentration of the reactant as high as possible. High concentration you get in PFR. Therefore, generally PFR should be used. Then if there is again a mixed reactor of small and large, then you have to use a small MFR. If there is no small, then you can go for a large. So if your order is greater than 1, generally PFR should come first because your concentration should be as high as possible. This is what yesterday I'm just talking, right? So in CSTR, what will happen is your concentration is suddenly decreased. Your concentration is suddenly decreased. But in PFR, what will I'll just write here so that so you can see here. I'll just do thing. Now this is PFR. So in PFR, what is happening is the concentration is gradually coming down. So if you see the curve, the CA curve will go like this, right? So slowly it will reduce because this is the length of the reactor, length, right? With the length. Whereas in CSTR, what is happening is this is CA naught, which is having a very high concentration. This is CA, and this is also CA. This is the mixing. So what will happen? The concentration from CA naught, it is suddenly dropping to CA. The moment it enters here, suddenly it is dropping from here to here. So all of a sudden it is dropping. Whereas here, there is a gradual change because there is no mixing at all. No mixing. But here, due to the complete mixing, there is sudden drop in the concentration. You know that concentration is minus R is sorry, minus R is K into Ca power. Sorry, see what is happening here. Let me write here. Okay. This pen is not good. Minus Ra is K times Ca power n. So R changes as your concentration. High concentration, high will be the rate. Low concentration, low will be the rate. Therefore, here the concentration of A is very high because it is smallly decreasing. There is no mixing. Though A is very high, therefore the reaction rate will be higher. Therefore, your conversion also will be higher. Whereas here the conversion is from Ca naught, very high concentration, it is coming to Ca, which is very low. It's all of a sudden, immediately. Therefore, very low concentration. You have rate also. See, concentration. Yeah, where is this? Yeah, concentration is low. Therefore, your rate also will be low. This is the reason why rate is low. Again, the conversion is low. This is the main reason why you get PFR more what do you call conversion than CSTR. It's all because of the concentration inside the reactor. In MFR, the concentration will suddenly decrease, whereas in PFR, there is no sudden decrease because of no mixing. So here mixing, whether it is bad or good, in mass transfer, to enhance the mass transfer rate, mixing should be done. But here in reactor engineering, if you mix it, then what will happen? Your concentration will suddenly drop. So there is that mixing plays a very important role. Again, what type of mixing is done? Either it is late mixing or early mixing. There are again different things which you will study in the fourth. I think this is the fifth unit. That is the non-ideal reactors. Whether the mixing should be, because there are some reactions where the mixing should be immediate. There are some reactions where the mixing should be later. Again, early mixing, late mixing, again, micro mixing, macro mixing. This is all, I'll give you one example so that you will remember what is this early mixing and late mixing. I'll give a cooking example so that all the people will understand. You take a upma, what upma, this Bombay Rava upma. What you do for doing the upma, I know some of you know. If you don't know, just listen. Again, don't think that I'm teaching cooking here. Cooking is an art, right? If you know chemical engineering, especially heat transfer, mass transfer, and all, you can do excellent cooking, right? That does not mean that chemical engineers are a good cook and all. Just to make my point clear, I am just giving that. Okay. Take CRE, I'll do my entire CRE2 course with only that gulab jamun, right? It's a beautiful example, gulab jamun, right? So the example what I'm going to give is upma, right? So there are 2 or 3 types of upmas which you can do. One is Bombay Rava upma, then you can do with the Goduma Rava also, and you can do with the one more that what is that noodles type? What is it? Favorite? What do you call that? Semia. Yeah, semia. Let us come to Bombay Rava upma. In Bombay Rava upma, you mix all the ingredients and fry it, and then put water. You boil the water, right? Once you boil the water, what you do is you will be slowly putting this rava mavu inside and then stirring it immediately, right? If you're not stirring immediately, what will happen? This fellow, rava fellow, will form as a globule, and big undas like inside, like round balls it will have. It won't, the concentration will not be uniform at all. You can do if you want, right? If you don't mix it, it will happen that. So you won't get a homogeneity. In between, there will be a lot of big balls, small balls, where there is no mixing at all with the water, right? That is called as early mixing. And if you mix early, what will happen is you get a very good consistency or concentration, the uniform concentration. Your upma will be everywhere same taste or globule or whatever, even small things, it will be there, right? It will be cooked nicely. What will happen if you're not mixing it? If you're not mixing it, then what will happen? If you take at the edges, there may be some properly cooked, and if you take at the center of that vessel, that upma, you will have some globules, big balls, where inside it is not cooked at all. You won't feel like to eat at all. So there are some reactions where the early mixing should be done. This is one example I gave. Now let us come to late mixing. There is one more mixing called as late mixing. What is that? Now you take the same example of upma. Now you do with semia or even Bombay Rava. I don't know whether you are well versed with it. Again, Bombay Rava also is same like upma. When you are adding this Bombay Rava, just like that upma, no need to mix. You just put entire thing inside, and your mother will leave for some time. What will happen during that time? The Bombay Rava, which is big particle, is bit bigger than this what do you call rava, that Bombay Rava. Slowly the water will penetrate inside, and then it becomes big. The size becomes big. In that process, what will happen is slowly the water will be sucked by this particular that Bombay Rava. Then after sucking, then you start mixing it. So for this kind of thing, no need to mix early. You can mix even early. You can mix if you want, but no need of that. So in reaction engineering, it is better to avoid mixing, because the moment you mix, what will happen? The concentration becomes uniform. When the concentration becomes uniform, you won't have a gradient. you should have that gradient, right? From higher to the lower concentration, then your rate will enhance. But in reaction engineering, if you mix it, it becomes uniform. Therefore, your rate will not enhance. Understand? The same thing with upma also. That other upma, what is that? Semia. Semia also, even this, what is the Maggi noodle? You put inside in hot water and you leave for some time, because then it becomes bulge, absorbs all the water and becomes nicely cooked, and then start mixing early, later. Correct? So that is what is the early mixing and late mixing. That is the main reason why your CSTR is having lesser conversion than that of PFR. Does it make sense? Yeah. I can ask some questions. Otherwise, we can go to the second answer. That is problem. Does it okay? Or you want still more examples? Emma? No one is answering anything. Arun? No, not Arun. I think his name is Arjun. Arjun, you are there? Arjun. தம்பி என்னப்பா யாருமே எதுவுமே பேச மாட்டேங்கிறீங்க?
Sir, thank you.
Who is this Arjun? Who is talking? Guru, only you are talking. No one else is talking. Everyone is sleeping. CR is sleeping subject or what?
No, sir.
Is it? Does it make sense what I showed? What I told? Why this CSTR and PFR?
Sir, Arjun absent, sir.
Enama? What happened?
Sir, Arjun is not in the meetings.
Okay. Arjun is not in the meeting. Okay. For you, it is okay, ma? Who talked now? Because I am unable to see who talked. Who
Yes,
talked,
sir,
ma?
okay.
Mati, Watani. Okay. Good. Okay, you understood, right? Shall I go for the next problem? Shall we see?
Yes, sir.
Okay. Then.
Yes, sir.
Thank you for your feedback. Because this continuous feedback will make me to get interest, and then if I know that students are listening, then I can teach much. If you are not listening, then we also get, anyhow, people are not listening. Let me finish off the subject. If you are listening and if you are asking questions, I will give you excellent examples in CRE. Right? Because the professor who taught me, Professor Krishnaya in IIT Madras, really is a gem. He gives examples in such a way that you will never forget the concept in your life, entire life, even if you are not studying this CRE subject. You know, that kind of examples. One is, I should not tell that example, cigarette example. Beautiful example of catalytic reactions. It will come in CRE2. Gulab Jamun example. Traffic, this signal, traffic signal, you will stop, right? There, that examples. Wonderful examples he used to give. Q, Tirupati Q. For a PFR is nothing but a Q. In Tirupati, if you once go in a queue, the fellow who is going first only see the God first. Beautiful examples he used to give, right? If you interact with me, then I'll give excellent examples. If you're not interaction, that thing it will lose, right? So again, I request you to just interact so that I feel comfortable and give out with a lot of, I share my own thoughts and my experience with you. This subject I'm teaching from past 24 years now. Right from 98, I'm teaching this subject. In between some years I didn't teach. Right? So please try to take the opportunity to talk more about CRE. That is why I didn't give the answers also, because I want you to talk CRE with your friends. This is what my professor did to us in when we studied in IIT Madras. He never gave the answers, you know. He will ask us to debug in the net or something like that, search books. So he used to create too much curiosity in that subject. He used to just give some open-end question and he will ask us to find the answers. And we used to have a good set with our friends, peers. We used to even just like one example earlier, one advertisement: sleep cricket, drink cricket, and something cricket in '99 World Cup. During that time it came. So he used to tell that eat CRE, drink CRE, like that, talk CRE. Wherever you are, just talk. If two chemical engineers are there, you have to talk CRE. That's his motive, right? So he's a great professor. So he's still now in IIT Tirupati. He's the mentor for it. The great professor. If you are happening to see some video lectures of him in NPTEL, there is a video lecture CRE. Just listen to it. At least one class you listen. Really, you will feel very much motivated, because that's how the power of his teaching, right? So I'm fortunate to listen to two of his classes, two of his whole subjects, CRE1 and CRE2 both, right? Okay, let us do the second problem. The kinetics of liquid phase decomposition of A is studied in two MFRs in series. So here, earlier case, it is one PFR. Here, two MFRs in series. And the second unit is having twice the volume of the first. So twice the volume liquid phase reaction is giving you. So you know that one big CSTR and a small CSTR is there. You always better to connect one small CSTR and then big CSTR, because early, why? Now you should tell me, because one slow CSTR, less CSTR, your conversion, your concentration will be less reduced, whereas big CSTR, your concentration will be still reduced. But in reaction engineering, you want to have your CA as high as possible. Understand? So definitely your small CSTR should come first, so that your CA will be a bit comparatively higher. Understand? So try to get now whatever we talked earlier in terms of only these two. That is, you want to keep your CA very high compared to that of other things. If you can keep CA high, then your rate will be high. Rate is high, your conversion also will be higher. So out of the two reactors, small reactor and big reactor, definitely your CA will be high in small reactor than the big reactor, because CA is high in the sense the big reactor, your tau also will be more time it is spending inside the reactor. More the time it spends inside the reactor, especially CSTR, your more mixing will happen. Therefore, your concentration becomes uniform. So you won't have much of the conversion at all. So at a steady state with a feed concentration of 1 mole of A per liter. So he's giving you FA naught. And mean resistance time, he's giving you the tau or T bar, because here this is liquid phase. Therefore, mean resistance time and tau, that is the space time, is going to be the same. But if it is a gas phase, mean resistance time is T bar, whereas tau is V by V naught, right? So 96 seconds in the first reactor. The concentration of A in the first reactor is 0.5. He is giving you the concentration of A. Initially, it is this. Final, it is after first reactor, it is 0.5. And in the second reactor also is giving you. That is CA1 is giving you. CA2 is also giving you. Now he's asking you to find the kinetic expression, right? So he's not asking you to calculate the conversion or something like that. He's asking you the kinetic expression. Kinetic equation, that is nothing but minus RA is K into CA power N, is asking you what is the N and K. Understood? Shall we go for the solution? Yeah, I'll go for the solution now. This also one more problem you can just look at. I'm skipping this just to concentrate on only on these problems, because these are the problems which they ask in the exam. So that is why I'm just concentrating on that. So next problem you can see here. This is the problem which he is asking you. The kinetics of aqueous phase decomposition of A is investigated in two mixed reactors in series. One second unit is twice the large. At steady state, a feed composition of 1 and a residence time of 96 in the first reactor. CA1 is 0.5 and CA2 is 0.25. Kindly find the rate expression, right? So this is what he gave. A gives product. We don't know what is the order because he never gave it is elementary reaction or something like that. He just gave aqueous phase. Therefore, it is a liquid phase. No need of calculating the expansion factor. C naught is initial, C1, C2, V1 and V2. Right? V1, V2 is twice larger of V1. That is what is giving. So C naught is Ca naught is 1. C1 or Ca1 is 0.5. C2 or Ca2 is 0.25. For the first reactor, this is a series. This is a CSTR. So in first reactor, R1 tau 1 is C naught minus C1 by R1. Correct. This is tau by C naught is XA by minus RA. Right. So the rate is given by minus RA is K into Ca power n. So R1 is K Ca1 power n. We don't know what is this n and K. We need to find out. So substitute RA here. Tau is C naught minus C1 by K into Ca1 power n. Like that second reactor also tau 2 is this. But he gave what is tau, right? For mean resistance time is 96. So for a liquid phase reaction, your space time and mean resistance time is same. But for a gas phase reactions, space time will not be equal to mean resistance time. Space time is nothing but V by volumetric flow rate. That is volume by volumetric flow rate. You have to put mean resistance time is nothing but T bar. So volume of CSTR 1 is V1. Volume of CSTR 2 is 2 times V1. So it is twice. So when you know 2 taus, so substitute 1 by other. Tau 1 by tau 2 is nothing but volume by volumetric flow rate of 1 divided by volumetric flow rate of 2. So we can calculate tau 2 based on tau 1. Tau 2 is this particular thing into tau 1, right? So this particular thing is nothing but 2V1 by V1. That is what he gave 2 times. So into tau 1. So tau 1 is 92. So tau 2 becomes 192 seconds, right? Because it is twice. So you are understandable that your tau also becomes twice because the area is more or the volume is more, tau also becomes more. So there are two equations here, 1 and 2. So what you do, you try to divide A by B. Tau 1 by tau 2 is C naught minus C1 by this. This is tau 2. So if you divide this, C naught minus C1 by C1 minus C2 into C2 by C1 whole power n, KK gets cancelled out, n you are getting. We know all this. We know tau 1, tau 2. Calculate n. You can calculate n, right? N is 2. The order of a reaction is 2. Because we know the rest of the thing. So K we need to find out. For calculating K, you either substitute in one of the reactions and then find out K, right? Because tau you know, T also we know. Then you can calculate K. K you find out any of that reaction. K is this much. Because since order is 2, K will have a unit of concentration power 1 minus n, time power minus 1, concentration power 1 minus n, n is 2. Therefore, concentration power minus 1, time power minus 1. Concentration is mole per liter. Inverse will be liter per mole into second. That's what. So the kinetic expression is this particular thing. Kinetic expression is this. Okay. Yeah, any doubt? This is a simple problem, actually. This is the simplest of the problem. Any doubt, man? Yeah, we'll go to the third problem. If you see, just listen to the third problem. A liquid reactant stream with Ca0 is 1 mole per liter passes through 2 MFRs in series. So 2 MFRs are there in series. The concentration of A in the exit stream from the first reactor is this. So Ca1 is giving you. The concentration of A in the exit stream in the second reactor. Find. You have to find Ca2. Reaction is giving A gives R. Follows the second order kinetics. V2 by V1. That is the volume of this particular thing is twice. The same thing problem. Just we did this problem just now. The same type, right? You have to calculate V2, right? Ca2, right? Okay, like that, you can see that the fourth problem, an aqueous reactant system with Ca0 is 4 mole per second, passes through a MFR and a PFR. Passes through MFR followed by PFR. Find the conversion at the exit of PFR if the concentration of A in MFR is this particular thing. So Ca1 is giving you, he is asking you to calculate Ca2. The reaction is second order with respect to A. The volume of PFR is thrice that of MFR, right? So PFR is followed. MFR is followed by PFR. So MFR first and PFR. But in actual, it should be first PFR, then only MFR, right? So he's asking what will be the concentration at the exit. It's also same, right? So you can see here, this also problem. Elementary irreversible liquid phase reaction. This is thing elementary is giving. So second order liquid phase takes place in PFR using equimolar A and B. Conversion is 90%. I think this is the same thing, na, which we got in first. Yeah, I think 1 and 5 is same. Yeah. So if MFR 10 times as large as PFR were placed in series with the existing, which reactor should come first? I think this is the same of 1. Yeah, no need to do the repetition problem. Just write for 5 is repeated, right? In your assignment. Just write put 5 and then repeated. Okay. So you can see here elementary liquid phase reaction. RA is giving you liters per mole minute. CACB, so second order, is carried out in an experimental tubular reactor with the following conditions. Volume is giving you, volumetric flow rate is giving you, then you can put volume by volumetric flow rate to give you tau, right? The conversions, concentrations of the reactant Ca0 and Cb0 is this. What is asking you? Find the fractional conversion of the reactant that should be obtained in a PFR. What is the XCA is asking you? But the same conversion in part 1, find the size of MFR required. So what you know the conversion here, for the same conversion, what will be the size of MFR? You know that the size of MFR will be much greater than this. Is asking you for the same conversion, what will be the size of MFR? You can do that, right? Find the conversion that can be expected in a MFR, which is equal in size to the PFR. That is PFR is 0.1. MFR is much higher, it will come. He's asking you if MFR size is 0.1, what will be the conversion? You know what will be the conversion in a what do you call PFR here? You are definitely the conversion for the same size will be coming lesser. That you can show, right? So try to do all these problems, and if any difficulty is there, please inform to me. So I think like this, a lot of problems are there. You can do all the problems. So most of the problems are similar, either CSTR arrangement or one big PFR, one big MFR, small MFR, or PFR, 2 PFRs in series. What should come first? What should come later? I think with the explanation what I gave, I think you can do that problems. I don't think you'll have much difficulty. Only one topic is remaining. That topic is recycle reactor. That we'll see in the next class. The next class may be as you whenever you want to give. That is, I think on Saturday. We'll see on 9:30 to 8:30 to 9:30. Yeah, that's all I want to talk today. I think Guru, you can take the attendance. 58 people are there. Yeah. Any doubt? You can ask. Yeah. As you think earlier. Yeah. Talk CRE. Think CRE. Think CRE. Good subject. Discuss CRE with your friends and come out with some good what do you call? Good questions. I know you will get any number of questions, right? Some crazy questions also you will get. Yeah, try to ask. So some crazy questions, even some questions I may not even answer. I'm openly agree because CR is that I use and you cannot visualize what is happening inside the reactor. Whatever you visualize, If you can visualize what is happening, then it is fine. Okay then. So come out with some good questions, some doubts or something like that. It's open. I like you asking me the questions, even any stupid questions also, no problem, right? It's just to learn only, right? That no question is a stupid question. Understand? That question, maybe some basics if you don't know, some stupid questions you have to put questions to yourself and then answer that questions to yourself. If you feel justified, then it is correct. That itself is very difficult, you know. That's not that easy to justify yourself. Understand? So try to put questions to yourself and try to find the answers to yourself. And if you feel the answer what you got is your heart is telling okay, then it is fine. But still, I don't think if you are very strong with the basics, then definitely you will find the answers and justification and all. Right? So try to ask some questions, even it is stupid, not a thing. Even a basic question also you can put. I'll try to answer as far as I can do. If I don't know, I'll just ask you, tell you that I don't know. We'll search together. Okay. Thank you. Stop the recording.